Now we're going to go from 5-axis to hole making because we've added a new method, new hole type method, and that is called rigid tapping. Now, rigid tapping, if your CNC controller supports what we refer to as canned cycles, C-A-N-N-E-D, as in a can. So these are predefined cycle types in your CNC machine that you can apply as needed. So this is an additional cycle type that we've added. It is a G84 cycle. And what we're doing here is if you're unfamiliar with rigid tapping versus regular tapping, so basically the difference is in the tool itself. In rigid tapping, the tool is rigid. In other words, the holder, the thread, everything is one rigid unit. Okay, so the movement of the threading, the cut feed, and the Z-dip is all controlled in the spindle and in the cut parameters that you're outputting. Okay, I should back up and say that I should reword that. If you're using the rigid, then if you look at the can cycle over here, it outputs the requirements for the controller to calculate the feed rate, the cut, and the
RPM is most important, the spindle RPM.
Yeah. So in the regular tapping, the tool is actually a floating tool where it does I guess the tapping inside that floating area. But there's one thing you need to know about this. The rigid tapping is a lot more accurate. Okay. And but there is one thing you want to be concerned about. Because it's rigid, you want to make sure you got your parameters correct because it puts more stress on the tap tool itself. So Joe, you want to add any more to that? I know it was kind of awkward explanations, but
no, go ahead. I think it's too hard, too difficult to explain it by words, so you need pictures. So
okay.
Go ahead.
So let's just to recap there. In hole making, there is now multiple options for tapping, and I'll show you that one on this part. Okay, so you got a rigid tap, that's the new method, and then you had your previous methods, which was a regular tap, and we'll show you that.
Sure. Yeah.
Okay, so we're going to start with 2.5-axis milling, and the part that we see here, the main thing that we added, well, one of the things we added is cutter compensation for hole pocketing and profiling. I did just want to mention that if you have a hole that you need to cut and you need very tight tolerances, up to 6 or even higher if you need it, hole pocketing and profiling is the way to go. You can get very tight tolerances, like if you got a press fit or a loose fit, say of a bearing or a sleeve or something. This is the method you want to go to. And now that we've added cutter compensation, it makes it even better if you're cutting production holes or just if you want to use the compensation feature in your controller. But we've added cutter comp for hole pocketing. On the left, you see hole pocketing. On the right, you see hole profiling. And over here in the dialog, it works exactly the same way as other cutter comp and other 2-axis operations. Just turn it on, and when you post, now I do want to make a mention of the post for cutter comp. Cutter comp does have to be set up in your post in order to output the G40, G41, G42, etc. In your G-code file. So if you're posting and you're looking for it and you don't see it, just contact us or send us your post definition file, and we'll add those criteria to it and send it back to you. So what we have is a basic 2-axis part, and we've got this hole pattern. Well, what we want to do is we want to tap these holes using a rigid tap method. And in a rigid tap, rigid means that the tap tool and the collet on the tool is rigid. Okay, it's like one solid tool. And the also I want to mention that the rigid tap is a CAN cycle. In other words, it's one of the cycles that's built into your machine controller. If your controller supports CAN cycles, then you can use these to do drilling, tapping, boring, etc. Those are all CAN cycles that's built into your router that we can take advantage of when we post out to the G-coded cell. So what do we have here? We have a rigid tap cycle tool path. Let's take a look at what it looks like. So we're selecting the 4 holes. Okay. We're using a rigid tap tool. Let's take a look at what that looks like. Okay. So this is our tap tool. The pitch is 0.041. Okay. And it can be a single thread tool or a multiple thread tool. Okay, I believe either way it should work fine. And this is the critical, as we did in thread milling and looked at the thread milling tool, the tap tool. Your thread pitch is the most critical dimension that you need to make sure you meet. Obviously, your tool diameter, etc., needs to be match the threads that you're tapping. But you know that should all be taken care of if you buy, what is this, a 3/16 or 1/88 tap tool or 3125 tap tool. All those dimensions will be in your spec sheet for the tool itself. So there's the rigid tap tool, and what the difference is here on the cut parameters tab, you'll now see that you have a rigid tap selection in the tapping types that you can pick from. So we have a tap, a PEC tap, a rigid tap, and then tap 1, 2, 3, 4, which are user-defined cycles that you can define yourself. What we're talking about here is a rigid tap motion. So we're going to pick rigid tapping. The depth is 1/4 inch. The location of cut geometry is at top. Okay, the curves are at the top of the hole. The dwell, we have it set, we have it turned off. And for the tap direction, we're doing a right-hand thread. We have an approach distance of 0.2, which means that the tapping tool is going to come down to 0.2 above the geometry, and then it's going to start tapping. And the feed rate is going to start going down on the z-axis to do your tap. Okay, so let's take a look at, let's cancel that out. Let's take a look at what happens in the post. So we got Haas rigid tap. Let's take a look at that. You'll see that down here in the cycles section, these are all of your CAN cycles. Okay, if your machine supports canned, as in a can, C-A-N-N-E-D, canned, so you have CAN cycles. If your controller supports CAN cycles, you'll be able to take advantage of all these different operation types in hole making. So here we added a rigid tap motion, and we have set up the cycle code here for a G84. All of this has been added in to create the G84 line of code, the CAN cycle code to post out to your router. If you don't see, this is not in there automatically in your post. If you want this added to your post, just contact us at support@MecSoft.com and we'll update the post for you. Okay, and let's see, that looks good. So let's go ahead and close that and post this out. Let's cancel that. Let's post. Okay, so we have 4 holes. We have a G84 CAN cycle that calls the CAN cycle on the controller. Okay, so you got 4 of them, and this is the line of code for your CAN cycle right here. Okay, so it's a G84. This is the X and Y location, the Z depth. Okay, this is the 0.2. This is the height at which the tap starts tapping, and then of course we have the feed rate of the tap itself. So this is one line of code that's posted out now that you can do for rigid tapping. Okay, that's it for the demo. Okay, let's go ahead and start the demo portion. The first thing we're going to take a look at is two-axis enhancements. So we've got a prismatic two-axis part. It's got a hole, a bunch of holes. One of the things that we're going to show you here is the enhancements in both the hole pocketing and in the thread milling. So in this part here, we have an M40 metric thread that goes through the base of this part. And in order to start that operation, or prior to starting that operation, we want to clear out, rough out the material, and get the inside diameter machined of that thread. So we need to do that ahead of time before we can do the thread milling. So let's go and look at hole pocketing here. So the first thing we're going to do is we're going to pocket out the hole and leave some allowance for the thread. So let's take a look at hole pocketing. Okay, so what we're going to do here was we're not going to select the whole perimeter, okay, because that doesn't represent the exact inner diameter of the thread itself. Okay, so we're going to select a point. Okay, we have selected a point right in the center. So we'll go on to the tool. So we're just going to use a flat mill, 12 millimeter diameter flat mill, to hole pocket this out. For the cut parameters on the hole pocketing, the enhancement in version 2025 that we mentioned is compensation. So now you can apply cutter compensation, right or left, on hole pocketing. So we got compensation set to auto on, and we've got other cut parameters set. A few that's of note here is make sure you select the location of your cut geometry. In this case, we have selected a point, okay? And that point lies at the top of the hole. It's not at the top of the part, as you can see, but it's at the top of the hole, and that is at top, okay? So also, we have a hole depth that we just used the measuring tool to go ahead and calculate that depth. And we also have a hole diameter. Here's where I mentioned that we didn't want to use the diameter of the hole as modeled because we want to make sure that we're cutting to the minor diameter of the thread, okay, which will be smaller in diameter than this hole itself. So we calculated that needed to be 39.796 in diameter. So that's the minor diameter of the M30 metric thread that we're going to be thread milling in that hole. Okay, so one thing to note, you want to make sure that you're using a point so you can specify the diameter. If you check this and use arcs for diameter, it'll just cut to the diameter of the hole itself, and that's not what we want. Okay, so what else do we have on here? Everything is pretty straightforward. We're adding a cleanup pass at each Z level just to make sure we get the, as much accuracy we can get out of the hole pocketing. Now the diameter of the hole pocket is not going to be the finished diameter. We're going to come back with a hole profile. So we can go ahead and go ahead and check that. That could be unchecked, but we'll leave it checked. Entry and exit. For typical for hole pocketing, we have a helical entry. So we got one helical entry at each cut level. So it's going to helical down and it's going to do a cleanup pass at each level. Okay, so we have a helix diameter of 1/4 of an inch or 6.35, and then we have a height H of 6.35. Okay, sorting, we're not going to do any sorting, we're only cutting one hole. And then also in 2025 we have feeder optimization parameters. We're not going to use those in this case. Okay, so let's just generate that. So we have a whole pocket. Okay, we got one helical motion, and then we have a cleanup pass at each cut level. If you look at front, okay, you'll see that we have a helical entry and then a cleanup pass. The blue motion is a cleanup pass at each cut level. So there's going to be 3 cut levels. Okay. Okay, so that is the whole pocket. So that's basically a roughing operation for this M40 metric thread, inside diameter thread. So based on that, let's go ahead and simulate that. Since we're at here, let's go ahead and turn the stock off. Now you will find that we haven't done any other roughing off, so you're going to see this hole stick up a little bit higher. Let's go ahead and play that. Okay, so we got the hole pocketing. Let's go ahead and look at the profiling. So in hole profiling, you have one helical motion to the depth, full depth of the hole, and then a cleanup pass at the base of the hole. So this cleanup pass is what really zeroes in the accuracy of this hole. So this hole profiling, let's take a look at that. We're using the same point, the same tool. So in the cut parameters, we have compensation on again, and we have location of cut geometry similar to the pocket at top. Okay, and the hole depth is the same at 19 millimeters. And then also for the hole diameter, we're using 39.796. That is the minor diameter of the hole. And we're going to uncheck use arcs, and everything else looks okay. Entry exit, we got lines and arcs, so we got a 1 millimeter entry, linear entry, and then also linear engagement, a linear retract. Okay, and let's see, that all looks good. No sorting, no optimization. Let's go ahead and generate that. So here is our hole profile, if you look at it here. So this is the minor diameter of the thread. Okay, so keep that in mind. We're not cutting all the way to the hole. Okay, so let's go ahead and show you what that looks like. So if you look at this is the M40 hole here on each side, and this is the helical motion of the hole profiling operation. Then we have a cleanup pass, circular cleanup pass at the bottom. And again, we have cutter compensation enabled. So now what we've got this set up. Let's go up here to isometric view. Okay. Let's change this view